right, so for starters, the quiz and the homework due dates are on the portal, and we will start section 6.4 on Monday, which is the fundamental theorem of calculus, which is a pretty big deal, and something that we will use to do all kinds of things as we go forward. So I want to talk about exploration too, but only the parts, honestly, that I want to talk about. Okay, it's the bottom line. All right, so there was this curve that kind of looked like that went from A to B. You were supposed to pick some x value. You were supposed to use horizontal lines and shade into the x value. You were supposed to write an integral for that area that was supposed to be the integral from a to x of f of t dt. I heard at least one group talking about why it had to be f of t dt or f of u du or f of w dw or whatever. But the bottom line is, in this situation, x wasn't really a variable. It was a point that you picked. So it can't also be your variable of integration. And then I think we were supposed to say that f of x was equal to the integral from a to x of f of t dt, right? I think we were supposed to like state that. We were supposed to give that area a name. Okay. And then they told you that the derivative of capital F was the limit as delta x went to 0 of delta f over delta x, which kind of makes sense because what is a derivative? The slope of the tangent at a point. Okay, so the slope of the tangent would be delta f over delta x because that's how we write slopes. And we turn that into a function for the derivative when we take that delta x to be really, 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 really small. Okay, I don't remember what number 6 asks. Sarah, do you have your book open? What does number 6 talk about? Okay, so I was supposed to like, what, draw some other segment over here? And then that was delta x. And then what's the height of my segment here? What's this height? It's not the x value though, it's the what? Yeah, and so what's the word I'm going to use for y here that involves the function? F of x. Okay, so for number 7, that height was f of x. So somehow, and then what does 8 ask you to do? Oh, the capital F prime of x. Okay, so for number 8, I have that delta F, nope, not delta P, that's third period. Delta F is equal to delta x times f of x. And I know why I think that's true. Anybody know why that's true? What am I effectively saying if I compare these two? Yeah, but what am I saying if I compare those two things? That these two things are equal, right? Okay, so let's back up a minute And we had, because this is really the point I want to make, that f of x was equal to the integral from a to x of f of t dt. And so if I take the derivative of both sides, okay, then I'm going to get f prime of x times d by dx a to the x of f of t dt. And it's this thing that's equal to f of x. Because, and this is the thing I want, this is why we did this exercise, was so that we could get to this statement. Correct. Because I am taking the derivative with respect to x. So if we look up here, capital F is the capital F is the antiderivative of this, right? Okay, it's the area under the curve. All right. So if I'm going to take the derivative of that with respect to x, this lower limit here somehow is going to be a constant, right? Because it's f of a constant. The x I'm holding in place temporarily. Like I'm saying, I want to pick this x value. I'm not saying x is equal to 4, like I'm saying a is equal to 0. I'm just saying I'm looking at this particular x value, or a particular x value, which eventually I'm going to encompass to be all x values. But when I take the derivative, whatever's happening here with this lower limit part is going to be a constant. And what happens when I take the derivative of a constant? I get 0. Okay, so that part's going to go away. And because I'm taking the derivative with respect to x, I pull out the f of x part. And so what this is supposed to be telling you is what I have said many times, which is that d by dx and the integral are inverse operators and undo each other. Just like sine and inverse sine, or squared and square root. And that's what I need you to walk away with. And so what this further tells us is that the integral of, no, the integral is the antiderivative of the integrand, which is something that we've been talking about too. Now you know how to take an antiderivative, right? Right? So if I told you that f prime of x was 3x squared, what would f of x be? Plus c, right? Because there's that constant, right? Because if I take the derivative of this, this could be x to the 3 plus a million. This could be x to the 3 plus pi. This could be x plus 3, x to the third plus e to the 100. Okay? And I'm going to get the same derivative. And that was a problem, a shortcoming that we had with the way that we were taking antiderivatives, is that you had to put that plus c on there. And what it gave you, we used the words, it gave you a family of solutions, which we'll talk about again after the AP exam when we do differential equations. But one of the nice things about what we've just learned and what we've just talked about with the definite integral is that it gives us a way to figure out what that c is. So let's talk about that for a minute before we do some problems. Okay? So I know, just to back up once again, I've got f of x is my integral from a to x, f of t dt. I could take the derivative of all of that, right? So I've got d by dx of f of x is going to be d by dx of my integral of a to x of f of t dt, and we said that that was going to be equal to f of x. Okay. Now this ends up looking a little weird, what I'm going to do next. But I'm going to take the antiderivative of this. And that means that what I'm going to get is, in fact, I am going to do that. I'm going to get g of x plus c. Okay? Where g of x plus c is really equal to f of x, but I don't know what f of x is because I don't know what that constant is. So it's like g of x is everything that f of x was unless there was a constant on the end. So it's the x cubed. But f of x is x cubed plus 4. But all I can get back is the g of x, which is x cubed. Okay? Make sense? You understand where I'm going here? All right. And when I take the antiderivative of this part, I get my integral. Okay. So what I need to do is figure out what that c is. Right? Okay. So what I'm going to do is I'm going to let x be equal to a. So this side is going to give me g of a plus c. So it's going to give me like whatever I got out of my antiderivative without the constant. And on the other side, I'm going to get the integral from a to a of f of t dt. Not the derivative. Yes, and that was one of the properties of definite integrals that we reviewed yesterday. And I did mention that you should think about it as if you're taking the integral from a to a so that the lower limit and the upper limit are the same, then you've got a rectangle that has a width of 0. Okay, so its area is going to be 0. Which tells you that that constant is equal to what? What? Negative, I heard somebody say it, negative g of a. So I've regained the value of my constant. And I can say that my definite integral from a to x of f of t dt is going to be equal to g of x, which again is what I got when I took the antiderivative, minus the constant. Okay? And so basically, we can substitute back in and find the area and find our constant. Okay? You're never going to write it out like this. You're just going to do it. So you know what? Let's just do it. Okay. So, page 295, number 21. We have the integral from 0 to 1 of e to the x dx. So this one is kind of to help us practice taking that whole antiderivative of the integrand. What? Yes. Yes. Now, because, so, all right, so let's start here. So the antiderivative of e to the x is in fact e to the x, okay? Because e to the x, the derivative of e to the x is e to the x, like Zoe said. Now, this is a definite integral, which means that I don't have to worry about the plus c, because I know what my lower and my upper limits are for the area under the curve, right? We could graph this if we wanted to. Say that again? Mm-hmm. Yes, but you're mixing a couple of different ideas together. So this is a different kind of integral because I know what both the limits are. So I can do this by I could do this by plotting my integrand. I think that's what I don't know if that's right? That's what an e to the x function looks like. Somebody back me up here. Right, it never hits 0, it's never negative. E to the 0 is 1. I think I'm pretty good. Okay. So what I'm saying here is I want to take this function and take the area under the curve from 0 to 1. Now, up until now, the way that we did this was to use some kind of geometry so that I could find the area under the curve. So I was making rectangles, I was finding things that I could shapes that I knew the area of. We also talked about doing this using your calculator. And we would have gotten the same answer whether we used geometric shapes under the curve or your calculator. Now, based on exploration 2, I'm telling you that there's a third way we can do this, which is finding the antiderivative and then evaluating it. And you're right that I don't know that constant, but I don't need to worry about the constant because I'm not trying to find the antiderivative for the sake of finding the antiderivative. I'm trying to specifically find the area under the curve. And then there's that funky symbol that reminds me that it's just a line. Okay, that reminds me that I have an upper limit and a lower limit, and then I need to substitute in and take the difference. So this becomes, I evaluate my function at the upper limit minus my function at the lower limit, which is going to give us e minus 1. Okay. When we get into the second half of this chapter, we're going to talk about something called indefinite integrals. And when we talk about indefinite integrals, then the purpose of this is to find the antiderivative, in which case it would be e to the x plus c. But I have a different goal because what I'm trying to do is find a formula that'll help me find the area for whatever values I choose later. What do you need? Who what? It's okay. Yeah. Mm-hmm. Just like when we first started derivatives, we actually found the slope at a point. We had x and y values that weren't just general x and y values. It was like find the slope to the tangent of the curve at 3, 2. And then we turned it into here's a general formula that I can use. Yeah, so that I could find that slope anywhere. And that's the same thing we're doing here, is your book starts with this very definite concrete idea of the area under the curve between two x points. And we're going to figure out how to do that. And then we're going to take a big step and say, okay, but what's the general formula that I could use all the time? Okay. All right. We feeling okay? All right. Again, in like by February break, you'll be solving integrals like nobody's business. It'll be easy. Okay. All right. So let's try another one. Let's try page 295, number 31. If somebody would read that one for us, please. All right, so this one brings together a whole bunch of different ideas. So we are supposed to find the average value or the mean value of the function. And you have a definition for that, right? That we went over earlier this week. So how do we find the average value of f? Using calculus. It's okay to look back in your notes. Okay. So B minus A is easy. What's that going to be? Yep, pi minus 0, which is going to give us pi. But we're also going to have to evaluate the integral. So everybody got what they need off of here? Okay, so I'm going to take the integral from 0 to pi of sine x dx. And we're going to solve this one using antiderivatives because it says we're supposed to. Okay, so what function has sine x as its derivative? Everybody think for a minute, so, and then we'll let you answer, okay? So think about it for a sec, because it's a little tricky. What do you got, Zoe? Negative cosine x, right? So this is going to be equal to negative cosine x. I like to put this step, and I don't know if your book always does, but I like to actually write down what the antiderivative is a little bit so that I can check. Okay? And also so that if somebody was watching what I was doing, they know that, hey, here's the antiderivative. I can pause for a minute and make sure I really understand that. Okay? So, and think about it. If we forget the negative sign for a minute, what's the derivative of cosine? Not sine x. Negative sine x. I told you had to memorize all those. Now they're coming back to bite you on the neck. Or butt. But I didn't want to say butt in a recording. But I did anyway. Gianni likes it. All right. So I've got negative sine times that negative sign gives me the derivative, which is what my integrand is. What did I do? Oh, sorry. Oh, yeah, but they were two, and usually I spell it. I do usually spell my SIGN signs, but I did not this time because I was still reeling from the fact that I said but on a recording. But anyway, so let's evaluate this. Do not use your calculators. So that's going to give me, and at the beginning, you probably want to write this out too. Okay, negative cosine minus negative cosine of 0. So what's the cosine of pi? Negative 1. What's the cosine of 0? So what's that going to give me?
0.
No! That's why you have to be careful and write it down.
It's going to give me 2.
That's why you have to write it down. Yeah, but that doesn't make any sense. Well, it's not just, it would make, well, yeah, but think about what sine looks like from 0 to pi. It looks like that. We did. We used it in exploration 1. Okay, but think about what do you think the average value of cosine is from 0 to pi? Probably going to be 0, right? Which makes sense because you've got half the curve above and half the curve below. All right, so let's go back to our statement for average value. So the average value of f, 1 over b minus a, the integral from a to b of f of x dx. So we said that 1 over b minus a was 1 over pi, and our integral was 2. So our average value was 2 over pi. It's not magic, it's math. Math is not magic. Okay. Yeah, no, not so much. Yeah, no, that doesn't make me feel good. The middle of January. All right, so we got time for one more here before you break my heart. Page 295, number 37. Somebody read it for us. from dx. Don't forget the dx. Okay. So what does the max min inequality tell us? That from A to B of f of x. Okay. So again, the b minus a we know. That's going to be 1. What do we need to find or identify? No. Yes. No. Yes. Effectively. Maddie. Plug what in? Okay. So I need to find this, and I need to find this, because my job is to find the lower and upper bounds of what my integral is. In this case, I don't care what its actual value is. I just want to know what it's bracketed between. So how do you think you're going to find the maximum and the minimum values of f of x? Set what equal to 0? Setting f of x equal to 0 would find where it crossed the x-axis, but it won't necessarily find me my minimum and my maximum values. Well, the derivative, hang on, okay, communication, and yeah, it is still wrong, but that's all right. That would give me places where I have maxes and mins. It does not necessarily give me the maximum and minimum values on the interval. Yes, you can graph it. Graph it.
I thought at first you were saying
Yes, you are. Cute is in the eyes of the beholder, because it kind of does that, right? Jeez. So here's 0 and here's 1, which is my interval, right? So that tells me that max f is going to be at f of 0. So that's going to be 1 over 1 plus 0 to the 4th, which gives me 1. Min f is at f of 1, which gives me 1 over 1 plus 1 to the 4th, which gives me a half. All right. We were lucky that the maxes and the mins were at the endpoints, but it's not always going to work out that way. So then we go back to the max-min inequality, and I've got max f, which is 1, times b minus a, which is 1 minus 0, less than or equal to my integral. Oh, sorry, min value. times my max value times b minus a. So this tells me that 1/2 is less than or equal to my integral from 0 to 1 of 1 plus x to the 4th dx is less than or equal to 1. Okay. I just want to get it all on there before the bell rings. We have physics now.